This
Okay.
conference will now be recorded. This conference will now be recorded.
So what I did was I put together a training agenda, which is based on what we kind of see as the flow of knowledge that is required for you to get ramped up quickly on the tool. Now, some of the quick introductions I wanted to get through was really help you understand what VisualSim is all about. So when I open up the front of the tool, you can see the all the documentation, the reference manuals, the training class material. Everything is right here on the front page. Similarly, there's a whole lot of library demos and application demos that cover all the different pieces of the tool, but and also a variety of applications. So kind of helps you accelerate a lot of your learning. Now, the best document to get started or do anything is the one right at the bottom here, called the quick reference guide, which I've already opened up right over here. Starts off with giving you a quick introduction and then goes into the GUI, talks about the documentation, and then talks about how the layout of the block is, and then goes into the different library blocks, the methodology, and then some of the more advanced. The previous release had about 3 pages. Now we extended this to 7 pages to pretty much cover everything in the tool. So quick kind of a quick background on the tool itself. The main thing that you have to know is that timing, power, and functionality are covered in VisualSim. And the key difference between this and some of the other tools would be some of them may be analytical, where it's more calculated, closer to an Excel spreadsheet, where you find the worst case execution time, or it's at the other end where you're evaluating the functional or the mathematics of an algorithm, which would be at the other end. So and we kind of fit somewhere in between those two, where we're trying to figure out what is going to be the implementation model for a particular design. The design could be controlled, could be algorithmic, or it could be a network, or any combination. The way we put it together is we call it communication, storage, and computation or computing. So that's the 3 different parts that go to put a system together. Now, these are, as I walk through this, these are some of the things that you typically tend to do with VisualSim. Obviously, sizing your system is very critical, looking at feasibility of a particular application to run on your system. The second part is looking at the power measurements and the power sizing associated. The third is focusing on the software, trying to figure out, how do I distribute my software across multi-cores or multi-processor, multi-boards, or even multi-boxes. And then looking at some of the other stuff, like things like failure analysis, safety, reliability, all of those kind of attributes as well. So this is a quick introduction to VisualSim before I get started. Now, one of the key things is VisualSim is made up of a variety of different documentation that's available in the tool. Again, I'm going back to the front page of the tool. And what you see over here is you see the installation guide, which is, hopefully you have everything installed, so we don't need to go through that. The getting started guide kind of gives you an idea of all the different possible modeling methodologies and all the different possible areas of analysis that are available, kind of gives you an idea of those. This reference guide here is kind of our 500-page document that has everything about everything. And the thing about it is that it you can get very detailed or snapshot, both type of information right out of the document. Again, as I mentioned, the quick reference guide is the most important document in the tool. That's that 7-pager that I started off with. Here we have the documentation for the libraries, for the regular expressions and tutorials. This is fairly important in the sense that all the library components are listed right over here. The tutorials are listed here, and the regular expressions. So this kind of covers all the content that you would need to actually assemble up a particular design or a particular system. Now, In terms of training material, the flow that I have today is kind of similar to the PowerPoint slides that you will see over here. So you can as I go through this, you'll find that it also has a kind of a similar order. That's a little more voluminous and it has a lot more details. In this session, I'm a little more concise. Now, going through the tool, there's the basic essence of the tool is a concept called a data structure. I'm going to open up a new window, and essentially the way you open up a new window is you do a file, new, and you do a block diagram editor. And what I'm going to do is I'm going to bring in a block called the digital simulator to say that, hey, I'm going to be doing some digital work. I'm going to bring in a traffic generator, and I'm just going to leave the default name for the data structure, which is a data structure is nothing but a struct in C, which has a field name and a value, a series of those. So what I'm going to do is just generate a single data structure to kind of illustrate what a data structure means. So that is the first thing we're going to do over here. I'm just going to set up a time for this, which is just the time at which I want the simulation to stop. Now I'm only running one. So it's going to find the queue is empty and it's just going to stop. So this is what a data structure looks like. What you're seeing over here is you have 6 different fields, and these are, by the way, the default fields. So any other data structure you create, we will tag on these 6 fields. And the reason we do that is a couple of different things. One is this tells me which block created it. So it's this name on the icon right there. The second thing is it gives me a sequential ID. If I start sending more of these, so say for example, I decide I'm going to send 3 of these. 3. Oops. Oh, sorry about that. I didn't set the distribution. So let me do that. And I'm going to get 3 of these. Okay. So I got 0, 1, and 2 seconds. I got it where this is ID1, ID2, and ID3. The third field that's important is the time field. It tells me what time this particular data structure was generated. So this is the basic element in VisualSim, the data structure. This is what flows through everything in a model. So if I open up another model, say something like this, don't worry about what the content of the model is, but as data flows through all of these, all of those are these data structures that are flowing through. As they flow through, it can, some of the blocks may modify certain fields, like here we are modifying these 5 fields. Some of them may actually use values from some fields, and others may remove fields. So it can be that, I'm just using the values, I'm modifying it, or I'm removing it. So I can, use any of those things. In this particular case, for example, I could even be using it to make decisions as well. So I can be doing any of those kind of things. So the data structure is kind of a basic element in VisualSim that flows through any model. So as we talked about, the field names and values. Now modifying field names really only happens in 2 sets of blocks. Now these kind of blocks here called the traffic blocks generate these data structures. Then we have a block called the expression list block and a block called the script block. And we also have the finite state machine. These 3 blocks can allow you to manipulate, which is change the value of the fields of these data structures. So for example, I could disconnect this over here, and I can go in here and I can say there's a field called index. So I'm going to say input.index. I'll give it a value 1. So, and then I'm going to connect this back up again. And when I run it, oops, I'm sorry. I need to remove these things because I get an error. Now notice that the index is now 1. So this way I can manipulate the values in a field of a data structure. Similarly, this block can be used, and I'll be talking about this a little bit later, but I can create a thing here, and I can say, create a new token, and I can call it header. And what this will do is it'll create a new data structure associated with a template called header. And header is a template that's already pre-stored, and those have those 6 values. So this is the basics of a data structure. And that's what flows right through the model. Of course, there are things where I can dynamically, as I showed you, create a new data structure. I can just add a new field. I can remove a field. So for example, over here, right back in here, I can go here and say input dot, and I can say new field, and I can give a value of, say, string. So I can, I can just essentially creates a new field in my data structure. So notice over here, I've got a field called new field, which is a value that is stored here. Now, the next step is to look at data types and polymorphism. So one of the key things in VisualSim is that when I go from, say, this block to another block, I don't have to worry about what is the data structure, what is the struct that is flowing through, as far as the fields that are required by this block are available. So I can just change this to another data structure, it's another template, and I can then send it across. And again, what you'll notice is that new field wasn't there, it created it, but now you can see there's a whole bunch of fields, but I didn't have to change anything. The reason is the blocks are polymorphic, which is it'll accept anything on the input, send anything on the output as is provided to it, and it will, it'll just update values or create new fields, remove fields, any of those kind of things. Okay. Now, what are the different data types? There's almost every data type that you can think about is available. So if I'm going to just open this to ports, and what I'm going to do is just open the types right here on the port, so you can see this Boolean, complex, double, fixed point, floating point, general, integer, long, matrix, object, scalar, short, string. You can have unknown, which means when it comes in, it figures it out. It has arrays, it has matrices, unsigned bytes. So it's got almost every single data type that you can think about is provided to you as standard thing as part of the tool. So that's the that's kind of the capability that you have these unbounded list of data types available to you. At this point, I'm going to stop, take a break, and ask anyone if anyone now has any questions. I'm just going to pause the recording.
This conference will now be recorded.
Now, apart from the data structure, there are 2 other attributes that are very important and key in VisualSim. The first 2 are the concept parameters and variables. Variables are similar to variables in C programming, which are things where you can use it, think about it like a single register position, and you can view it from different parts of the model. You can have, again, different types for these different data structures. So you have any combination of information you can store and then have it accessible in different parts of the design. Now, I'm going to go ahead and bring what's called a variable list. This is really where you define your variables. So now in the tool itself, there are 2 different types of variables. There's a local variable and global. Local means that it's only within that window, not below, not above, just within that window. Global means anywhere in the model. Even though this variable may be defined at the lowest level, it's still visible to the entire tool. Again, all the different data types are supported. I'm going to right click on the block. I'm going to go to documentation, get documentation. The reason I'm going to do that is because then I actually get to see all the different types. So I've got integer, double, arrays, data. So I can even define a data structure template, and it can be used. I can have an array. Now notice this is actually an array of data structures. So this is a mechanism to define an array of data structures. So it's really 10 processor DS data structures in this particular array. So it goes from 0 to 9. It can just be a data structure. It can be a string, Boolean, long, or it can be actually an expression, which is, I could have 1 + 1 + a parameter name. So it can even be something like this. So it can be all these different varieties of initialization values that you can start off your system, or start off your model with. So that is variables. Parameters are like constants in programming and C programming. The only difference is that parameters are something that you can keep varying and rerunning simulations. So they're constants that you modify across simulation runs. So for example, in this particular case, I'm going to go ahead and delete this. And then what I'm going to do is bring in a parameter, and I'm just going to call it clock rate. And I'm just going to give it like say 10. Okay. Now this becomes a parameter of the model. And here, what I'm going to do is for the value, rather than just entering in a value here, I'm going to type in that name here. And what it does now is that it actually links this value right down here. There's a process of exporting up the order. So now when I do this, and when I run the simulation, what you'll notice is, and I'm going to go back to the original one, which was header, because it's a smaller data structure. So earlier on, if you remember, it came out as 0, 1, and 2. Now you notice it's coming out at 0 and 10. There's only 2. We were expecting 3 here, but only 2 came out right over here. The reason being is we're running the simulation only for 10. So if I change this to 30, run this, you can see 0, 10, and 20. So earlier on to 0, 1, 2. Now because we changed this clock rate to 10, it becomes 0, 10, 20. Similarly, I could change this to 5.5, and I get the appropriate changes. So the reason this is important at the top level is because of the fact that now I can run this from what we call our batch mode simulation or our command line simulation. And this allows you to actually run simulations from the command line and distribute it across a server farm or even across multiple cores in a system, where it allows you to run multiple simulations in parallel without you having to actually interactively work with the design. So the parameters are the ones that you'd keep changing. Also, if you want to hand over a model from one person to another person, you can just have these top level parameters, so the user can just start off and simply just change parameters without worrying about anything else. So that's the use of parameters. The parameters are constants, while variables, and I'm going to just define a variable here. I guess we got 4 of them. 1, 2, 3, 4. So I'm just going to use my mem3, which is right over here. So I'm going to double click on this, and I'm going to say my mem3 is equal to 64. That's 0. Okay. So I'm going to go ahead and run the simulation. Notice here nothing changes over here because the memory is kind of an independent thing that sits on top. I'm going to do what's called a listen to block on this, so I can actually see what's happening. So I can put this over here, and when I run this, what you'll notice is when the data structure comes in, it does all this processing, and notice right here my mem3 became 64. Now, question is, do I always have to do this? No. You can actually go in and get one of the utilities that are available to you. So we've got a variety of utilities, and you can get what's called a variable dump. So we'll click on this one over here. It brings in this diamond. I can put it over here. And remember, I have to connect this. I can't just run my wire over it. I essentially have to connect it. So what I'm going to do is I'm just going to connect this to this. I'm going to copy paste this. I'm going to output it. I don't think this has any values. It doesn't have any variables. I'm going to run the same model again. Now, what you see over here is this shows me all the possible different arrays that are there in the system. I'm sorry, all the different variables. But the one that we're really interested in is this mymem3. So as you can see, there is mymem3. So this is generated as a data structure, out of which I can get this field called mymem3, and I can see what the value is. And you can see right through, every time the data structure came out, it was triggered, and you can see all the different arrays within the particular tool. Okay, so what you essentially have now is you've defined a clock rate, which is a parameter. You got a variable right over here. Now, what I'm going to do is I'm going to go to the next level. And oh, before I forget, this thing over here called the relation or diamond, the black diamond, is to allow you to connect multiple wires to a single port. I'm sorry, to a single thread. So this one, and this one needs to be connected, and I can connect it using this diamond. Now, if I want to make a wiring connection, I'm going to disconnect this. I want to make a wiring connection from the diamond. If I click on it and I keep moving, it'll keep moving here. So what I need to do is I need to hold down on my control or my command key on the Mac, control on Windows and Linux, and then I can, drag, hold and drag with my mouse, and I can connect to the other one. Now, notice, oops, I got an extra one. Now, when I make the connection like this, notice it's a thin line. Run it over the port here, it becomes a thick line. So this is how I know that the connection actually has been made. So this is how ports work in VisualSim, and this is also how the diamond works in VisualSim. Kind of running ahead, but I thought I'd bring it up here. Now, let's go back to what I wanted to do first, which was, I wanted to go in here. I'm going to select these blocks, including the wire that's connected to the rest of the system. And I'm going to go create what I call a hierarchy. A hierarchy is right over here, is something where I have a block that contains, or a container that contains additional components within it. So now what I'm going to do is when I go inside, I can do what's called an open block. So when I do an open block, what you notice is I've got this thing here. Now you also got to notice something else, which I didn't actually bring in. You remember the clock rate over here? When I did the create hierarchy, this clock rate also ended up here. The reason is the clock rate is a parameter of this block. So anytime any parameters are visible, oops, sorry about that. Parameters are visible, let's minimize all of those things. It's going to actually provide this parameter. Now, how do I link this one up to this one here? What I can do is I can go double click here and I can write clock rate. Notice clock underscore doesn't exist as a parameter. It says ID clock is undefined. This is some of our error checking while you're creating the model. So here, unless I end up putting this or I have, end up putting some other parameter, it's going to give me an error. So now when I do this and I say, okay, it's fine, everybody's happy. So now what's happened? I have clock rate here, which is linked up to the clock rate at the top level. So now I'm going to go ahead and run simulation. Okay. So what you see over here is the 0, 5.5 level. Now I'm not going to change inside of this. I'm going to change it right over here. And when I do that, notice it's gone 0, 10, 20. So now I can actually have a parameter at the top level and I can link it up to the process, to the containers below, which are called hierarchical blocks. And I can describe, I can have it, take the values from a level above. Now, I don't necessarily have to keep going to the levels above. I could just stay at that level and not link it up to a level above. That's, depending on my requirement, I can do that as well. Now, the next step is I'm going to, earlier on I used mem3, which is a global. Now I'm going to use my mem1 inside of the block here. Okay. So rather than using my mem3, I'm going to use my mem1, and it's in type integer. So I'm going to put 64, close this, and I'm going to run the simulation. And now what has happened is that, I've got this, this my mem1. which is it's a dot mymem right over here, which indicates that it's a local memory variable. It's not a memory variable for the entire tool. These are all what are called global memories. These two are local memories. Now, what has happened here inside of this, right, is that this mymem here is now become what's called a block memory, which means it's available only here, because this one is not visible. The memory that was defined over here, the mymem1, is actually not visible here, so it's actually created a local memory within this block called a block memory. So when I go back here and I look at this thing over here, mymem1, notice the value hasn't changed to 64. It's still 1 because it's a local memory that's only available in this window. So now I can go back here, can bring another expression block over here and connect this up, and I can make the mymem1 equal to 32. Okay, go ahead and run simulation. And notice now the mymem1 has changed. The reason is this is now local to this window. So mymem3 still gets changed from inside because it's a global view, but mymem1 is local to this window, so it's only getting changed when there's something in this window. Now, what you created here within this block is now called a block memory. So you have a global, which is to the entire model, local, which is only that window, and then block memory, which is only within a particular block. Okay.
This conference will now be recorded.
Okay, so now we're going to move to the next level, which is looking at the concept of time and size. Everything in VisualSim is measured in terms of seconds. So I want to look at microseconds. I would actually have to write, so if I want to put microseconds, that'll equal to 1.0 e minus 6. If I wanted to do nanoseconds, it'll be 1.0 e minus 9. So it's everything is in seconds, and then it's all relative to that. You create your microseconds or nanoseconds or whatever attributes you want. Now, if you go back to this model over here, you're going to notice some key attributes. One of them is TStop, and the other one is TResolution. TStop is how long your simulation runs, so which is taken from the top level simulator over here, okay, which is right here, which is the stop time. That's called TStop, and you notice it's a variable that can be used across the whole tool, right over here. And TResolution is right here from the top level again. So these are attributes of the tool. What do they mean? This means that it's going to be running for 30 seconds, and the minimum time difference can be 1 picosecond in this place. We can actually go to 1/100th of a picosecond, 10 to the minus 14 is where we can go, but in this particular case, we have the default set to 1 picosecond. So that's the notion of time. Now, this block here that we have called the digital simulator, the block we got from the model setup, and we have to have this block in 3 different types or 4 different types of locations. One is obviously at the top in any model. The second thing is when we're creating a class, and I'll be explaining a class later. The third one is where it's a dynamic instantiation block. Again, I'll be talking about that a little later. So those would be the 3 cases when I would actually need the digital simulator. Now, the fourth way is what I was going to start off with, is a couple of different places, is the composite actor. I can, if I want to, I can put a simulator here, but it's optional. Now, I could have a composite actor that is within a finite state machine. So for the states and transitions, I could have a block diagram within each of the states or transitions, and those are, you again could put a simulator in there. So again, top level of the model, any class block, any dynamic instantiation, and then the composite actor is optional when it's out in the middle, but when it's within a finite state machine, either as a definition for a state or a transition, you need to have the digital simulator. So that's on the digital simulator, and the 2 key attributes are the stop time, and the time resolution. Now, there are a few more things in the digital simulator, and I will bring that up a little later, but I'll just mention it. One is debugging, so I can get a macro debug of the whole tool. The second thing that's very important is these two fields over here. The first is now, earlier on, you had to actually view the statistics in the GUI, or you had to save it to a file or things like that. Now, if I checkbox this, obviously it'll run very slow, but if I checkbox it, it'll actually write all the statistics to, I'm sorry, it won't be slow, it'll just, at the end of the simulation, it'll take like a second or so extra. But it'll essentially write all the statistics to files. So these are your resources, your hardware components, everything. The statistics get onto your power manager, everything gets written to the file. Now, another one is check all fields. So this one is where I'm testing to see that all the fields that have to come in a data structure are actually available before the block starts executing. So this is one of the new features that these two are new features that have been introduced in version 19 of the tool, which is coming out in a few weeks. At least the beta is coming out in a few weeks, and this can be utilized for for experiment, for where you want to speed it up, where you don't want to keep checking the fields all the time. By default, it'll only check it like 4 or 5 times, and after that, assume that everything else coming in will be the same. But this says forces it to check it all the time, and this one actually will say write all the statistics to file. So these two are two. What does the digital simulator do? The digital simulator manages what's called the event calendar. The event calendar is the is what's called synchronous events between asynchronous times. So what that means is at any time there are a bunch of events that are going to be executed. They could be moving from one port to another port. They could be something being put into a queue. Could be any activity, but essentially an event calendar is something that where it has synchronous time and a lot of events happening at the synchronous time, and then there's a variable delay to the next one. So unlike tools like Verilog, where or even like tools like like your spice simulators or analog simulators, you will have every clock cycle. If I say 200 megahertz, every 5 nanoseconds, it'll actually do some processing. Discrete event simulators at top level do not need to have to execute every clock cycle. So there's nothing happening for 3 minutes, it'll just jump the 3 minutes. Now, it doesn't mean that everything that, the accumulation of the time is ignored. Rather, you do take into consideration just that you don't waste that much of execution power to execute those things. So that's what it is. So remember, it's the synchronous events between asynchronous time. So it's not a periodic time thing, but rather a variable one. So that's on time, which is in seconds. As you saw, microseconds, nanoseconds need to have the E-9 or E-6. The other concept in VisualSim is the data size. Now, why is this important? We assume everything in bytes. So when you put the number 1 for byte size, it means it's 1 byte. So eventually downstream, if you want to like actually model bit level, you got to do 1 multiplied by 8. Or if you want to do, say, you want to compute the throughput on, say, an Ethernet network, you'd have to have the one, if you say it's like 200 megahertz or 200 megabit per second, then it's actually multiplied by 8. I'm sorry, divided by 8 if you're using the bytes. So that's the byte concept right over here. Now that you learned some of the basics of the tool, let's start getting into some of the more detailed stuff. First and foremost is VisualSim exists because of all the libraries. And I'm going to talk about the libraries in the next section, so I'm not going to go in details, but remember, you can search for items. Now the search is okay, it's not a fantastic, but it still helps you. You can type in the word processor, and it will point you directly into the processor generator folder, and you can see the processor block right there. Now the other type of search is what's called a graphics search, which is right over here, where I can search for, say, a parameter, or I can search for a block name or anything. within the model. So it'll actually go through every level within the model and find out what is available. So, I had a block called traffic, which is inside of this block here. So I'm going to do a search, and immediately it found it. So when I did that, it clicked here, it opened this, and it highlighted that block. So I can very quickly just search for some particular thing, and it'll actually find it. Similarly, I can search for clock rate. And it finds, so here's the thing, it found the clock rate, which is this. It found the clock rate here, which highlighted this. And then it found the clock rate and highlighted here because the clock rate parameter is used over here. So it shows you where that item is utilized all over the model. Now, there are some limitations. So for example, if I type my mem, probably won't, oh, it does show you now. Okay, so that's new. The first is it shows me, this variable list output. The second is it shows me that it's being used over here. And the third is it's being used inside of this. And notice it didn't actually define the variable list here, but oh, I'm sorry, it does define it right over there. So that's the definition for that block over there as well. Just highlight it. So yeah, I guess now it shows everything that you're looking for. Okay. So the search is actually quite useful when you're trying to look up things within a particular model as well. Now, one of the key things to understand is a flow within a model. We're going to start with the flow within a block, and then we're going to walk on a flow within a model. So within a block, what happens is you can have something come in, triggers the block to start executing. The block does some functionality, whatever the functionality is, and then it comes out on the output port. Now notice this block has only one port. There can be other blocks. For example, I can go down here and go down to here and go down here. You can bring some of these blocks that have lots of input ports. So it might be an ANDing of the input ports. So in this case, the first four ports are ANDed. So I need 1, 2, 3, 4. I need these 4 ports ANDed. I'm sorry. I need 1, 2, and 3. I need these 3 ports ANDed. Only if I get all 3, it actually puts it into the queue. The others are providing informational data. That's all. But I do need these 3. So I can either be an ANDing of all the ports, or I can be an ORing of all the ports. So that is one concept. So it's this. Now, second concept is there are 2 blocks, the expression list and the script block, where I can add any number of input ports and any number of output ports. So when I can right click on this block, I can say click on ports. I can say click on add. I can double click on the space here, and I can say input 1, I can call it input, and I can just leave it general so the block will actually figure it out for itself. Similarly, I can go in, I can say add, I can double click, I can say output 1. I can click on output here, I can say, so notice I've got 2 of these. Now what's key here is with the expression list block, both the inputs have to arrive before the clock fires. Now notice in that queue block, what happened was we only needed the 3 ports that were ANDed to be available. The others were not required. So I can simply do this. Now, for the output here, I would have to type in something which I'm not going to do right now. But enough to say that I can either have something that does an ANDing, or it can be an ORing of the ports for use in the model. Now, we did talk about the wires here. So the wires are do not have any delays. They don't modify any values. They don't do any other processing. What wires do is essentially tells you that this port is connected here, which is connected here, 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 and here. That is all it's conveying. So the wires actually just move the data over to these different points. They don't consume time. They don't consume power. They don't have any other functionality. So that's a key thing to remember. This is not a wire as in physical hardware. It's just a wire that shows you where the data is going to be going to next. That's all it's showing you. Okay? This one here is a flow diagram. So you can see that data comes in here, goes here, it goes here, it comes out this way, it continues on to this block. So this is the flow diagram that you would see in a model. So this is the basic essence of how VisualSim works. Now, another mechanism of VisualSim is a concept where I'm going to open up a digital simulator. I'm going to bring in a traffic block. I'm going to bring in what's called a mapper block, and I'll explain this concept in a second. Connect this. I'm going to bring in a resource, which is called system resource. Just going to give this one of them is enough. I'll just say run this for 10, even though I know it's only going to run it for say 1 second. And then here, I'm going to just say, we're going to go to that one, which we'll call CPU. So which means I need to call this one CPU as well. And I'm going to say the task number is 1. I'm not going to worry about priority. If I leave this default, it means that it'll say, oh, everybody's got the same priority. I'm not going to worry about priority. So that's what this one is. Task time is a required field, so we'll just give 1.22 as a value. Okay. Now, what I'm going to do is I'm going to have again a text display. So I'm going to bring it over here. I'm going to go ahead and run the simulation. So notice here, we created this time at 0. Now remember, all of these, when it was created and when it was ended, there was a 0 time change. So if I ran this, oops, sorry about that, I got an error, which means I just have to correct this. Let's say output. We're going to discuss this a little later, so I'm not going to discuss this too much, but I will put this out. So now, where is this one over here? Okay. So notice here, started at 0.0, came out at 0.0. So no change in time. This model now started at 0.0, but came out at 1.22. So what's happening here? There's a concept, two concepts here. One is the separation of behavior and architecture. So this is your behavior flow. I've got a traffic. I've got something that's telling me what needs to be executed, comes out. Now this block here is the one that's actually executing it. So this flow here is this mapper block. Notice the triangle over here is linked to this triangle. So this one here sends it up here to execute and then continues it. The behavior flow by itself does not have any timing in this particular case. It depends on this block to actually put the timing into place. Okay, very important concept, behavior to architecture mapping, which is you have the behavior flow and then these are the resources associated with the system. Can be anything, can be an operating system, can be a CPU, can be a bus network, memory, cache, any other kind of an architectural component. Now, one of the key things over here, I can do a copy, I can do a paste, and what I can do now is I can actually run these, where both of them are going to go up here. So notice over here, the first one, which is this block over here, finished at 1.22. The second one came in still at 0.0, but it took 2.44. Execution time was still 1.22, but took 2.44. The reason is both of them came at the same time. They both ended up here. But what ended up happening was that this one got to execute first, which is this one here got to execute first. And this one here had to wait until this one completed before it started executing. So that is how the concurrency of time works. Now, what I could do is I could put two of these. I could call this CPU 2. I can have this block here, send it to CPU 2. So now when I do, two things have changed. First thing is notice yellow, yellow, and white and white. Second thing is both of them are finished at exactly the same time. So they're running completely concurrent and in parallel. So time can be completely independent. Every block could have its own time factor, you're not having a restriction on saying everybody should be off the same clock speed or anything like that. They can all be at completely independent clock speed. So for example, go back here and make it 1.33. Do that. Notice this finished at 1.33 is finished at 1.22. So they're all completely independent, or if I map both of them to the same device, which means they're both white and they mapped here, then I say 1.22 and 1.25. I'm sorry, 2.55. So it's 1.33, 1.22. So they can run completely independent within the tool itself. Okay. Now we did talk about the hierarchical block. Typically, the hierarchical block is used to better organize your system, because if I start putting these blocks out in a single window, it can start looking really messy, like something like this model over here. Just looking at it, I really have no idea. Of course, I've annotated it, but if I didn't, it's really, really hard to understand what's going on. That's why you organize it into these hierarchical blocks like we did for this model over here. Another concept is called dynamic instantiation. What dynamic instantiation does is it allows you to define a block once, and then at runtime, you can define how many instances of block do you want. Why do you want to do that? The reason you may want to do it is, say, for example, I've got 20 nodes. I don't want to instantiate 20 nodes, especially if they're all identical, just the variables are different. So what I can do is I can have a dynamic instantiation block, which is right up here. I can put this block out here, and it starts, at runtime, I can specify how many instances do I want. So I can set this up to 10, and then there'll be 10 instances of the block. So now if I go and look at an example, I'm going to pick up an example for this particular thing. So for example, this model over here, notice I've got a bunch of traffic, and then this block here has been described as being 500. Okay, so now I've got 500 instances of this particular block. Now, how do I say, when flow comes in, how do I say which instance to go to? That is where this block comes in. And again, it's in the same directory. It's called select instance, which is right over here. I can double click on it and specify which field says what instance number, and I can go 0 to n or n to 0. What that means is when it's going in, it's 0 to n. When it's coming out of this, you can say n to 0, which is bring it back into a singular flow. A lot of applications are used. For example, when I do multi-core architectures, I can put this to define each the cores. I can use this for, say, I want to have like 100 nodes on a network. I can describe this, and then I can have a routing table to describe the connectivity between all of them. So dynamic instantiation is very powerful. Of course, one thing is it does require, when I go into this, does require a digital simulator. This is very, very important. A digital simulator is absolutely required for you to use the dynamic instantiation. Okay. Another one is a concept called classes, which is, I'm going to create a class right now. The reason classes are important is class becomes a separate XML file. So say, for example, you described a particular algorithm, and you know that everybody else within Sandia is going to use it. And what you do is you describe it, you save it in a class, and you store it. And anybody else that has access to the library can now start using that block directly. It'll have its own set of parameters, it'll have its own logic, it'll have the input and output ports, it'll have everything. So for example, here's what I'm going to do. I'm going to take this. This is the procedure to create a class. Take this, create a class. Then what I'm going to do is I'm going to disconnect this interface. I'm going to go in here, and I'm going to say convert to class. So notice there's a halo that comes around it. Now I'm going to go inside of this block. So you notice this thing has happened over here. It's got all of this logic right over here. And now I'm going to go ahead and save as. And remember, it has to be either within the VisualSim install, or it has to be in an area that is defined under what's called a class path. So the base value, say C:/VisualSim/models, and then user library and something else. That first part of it must be in the class paths. So it can be that I'm running on Windows, so I say C:/VisualSim/new models. Somebody could be on Linux and say /VisualSim/user new models. And so that would be your baseline. So everything beyond that is what you use to describe the particular block. So it becomes very useful where you want to share it across multiple people. So this one here, I'm going to create a class, which is first step was converted into a hierarchical, remove all connections, convert to class. And now I open the block, and now I'm saving it. I'm saving the library, so I'm going to call it training model. But here's the key thing. I should call it save submodel only. So when I do this, now what happens here, notice a separate file was created. It's not part of the same block, but it's a separate file. I'm going to go ahead and close this. And I'm also going to delete this. I'm going to go in here and say instantiate class. I'm going to come up here, and I'm going to come in here, and I'm going to go into this. I'm going to use the library. We have training model, select it, it'll show up here, say okay. This block has now become available here. I can connect it up here, everything remains the same. I've got this block running. Now, I'm going to check what's happened here. So there are two concepts here. One is called open block, the other is called open instance. What is the difference? Open block opens it to where it is the original block, the original XML file. Open instance, you notice open instance has these halos. Open instance is the instance of that particular functionality within this particular model. Notice it says unnamed training model. So it's within this particular model. Now, key element, open instance can only be used for debugging. You don't want to go in there and modify the code or modify the block parameters, none of that stuff. Of course, if you had any parameters, you can change those values, but you can use this for debugging, which is right click on it and do some listen to block or listen to port, but not actually use it for for like going in and making changes. The reason is you want to capture the changes in the original location and not have to carry it through the particular, not have to have the user say, oh, you changed it in your model, but my model looks completely different. So changes are made in open block, not in open instance. So that's how classes work. As I mentioned, classes are very powerful because of reusability across projects, across models, any of those kind of things.
This conference will now be recorded.
So this concludes the first session of the VisualSim training class. We have now covered the basics of VisualSim, which includes all about what is available in VisualSim, the concept of data structures, the data types, parameters and variables, time concept, size concept, the simulator, and everything about the blocks itself and the basic concept of hierarchical, dynamic instantiation, and classes. With this, we will conclude the part 1 of our training class. Part 2 of the training class is going to cover the major list of library blocks that you would use most often. Thank you, and this is Deepak Shankar signing off from this session.